All right. So I have released the assignment 2 over the weekend. And as I had mentioned before, the assignment 2 is basically about implementing the various reduction strategies. In particular, the assignment 2 tests whether you can implement the normal order reduction, the call by name and call by value reduction strategies. Um, so the just to give you a hint, right? So the amount of code that you will write will be far less than the amount of test cases and examples that we have in that file. So if you know what you're doing, each of those pieces of functions that I expect you to write are 3 or 4 lines long for each one, right? So if you're writing more than 10 lines, you have to sort of stop and ask whether you're doing the right thing. Okay, so it's meant to be really small. It shouldn't take you a long time, but if you're writing a lot of lines, then certainly you're doing something wrong. Okay, so take that as a hint. So the thing to follow there is look at the earlier part of the semantics lectures where we describe the semantics very thoroughly using inference rules, right? So you'll be translating those inference rules into a program. It should be really short and really explicit. You will know what you are writing. If you're writing a lot of code and you're trying to you're poking around in the dark, you're not going to make progress. Okay, so that's my suggestion for that assignment. Okay. Yeah. So can everyone hear me? Yes. Okay. It might just be an issue on the students' side. Okay. Okay. So in the last class, we were looking at semantics. In particular, we were looking at semantics of encodings. And what we were looking at in the last class is how to encode booleans, right, in lambda calculus. So booleans are primitive data types. We encoded boolean values. We also encoded functions that operate over booleans. In a language like Ocaml, you also have other structures. In particular, we have the ability to construct new complex types. And a simple complex type is pairs, right? So what is a pair? Pair is just a tuple with 2 components. Okay, so here is an implementation of the important functions of pairs in Ocaml, right? So pair is a primitive. So Ocaml embeds primitive syntax for constructing pairs, right? So you can just do open bracket 1, 2 close bracket that will create a pair value with 2 ints. I can make it a little bit more explicit. I can say make pair is a function. Okay, so the function takes 2 arguments x and y and just returns you a pair. This is just so that we explicitly see that this is just a syntax over writing just a function like this, right? And then you have 2 functions. Those functions are extract, give me the first element of the pair, give me the second element of the pair. First, pattern matches on x and y, right? And then returns you the first element. And second, SND, pattern matches on x and y, and gives you the second element. So the thing to note here is make pair is a function, right, that takes 2 arguments, right, a and b, and then returns you a pair, which is a star b. First and second both take the pair as inputs and then return the first and the second component. Right? So if we want to encode pairs in lambda calculus, we want both the constructor, right, the way of constructing pairs, and the destructors. These 2 things which allow us to extract the components of the pair. So let's do that. So first we'll look at the constructor, right? So in Ocaml, if I tell you that the 2 components are f and s, the construction is just basically put them in this bracket syntax, right? Or use make pair function to construct them. In lambda calculus, we don't have any of these things, right? So we have to sort of explicitly encode them using using functions. And the way we represent pairs in lambda calculus is this encoding, right? So pair constructor is a function that takes two arguments f and s, right? Just like the make pair function. And the pair value itself is represented by this particular term. What does it say? It says it takes a single argument, right? And by convention, we will say that that argument is a Boolean, right? And applies this Boolean on f and s, right? Our encoding of a pair value is a function that takes a single argument, which is a Boolean, and then applies that Boolean on f and s. Okay, so that's our entire pair construction. Why is it a Boolean? Because the only thing that we want to do is to extract first and second elements of the pair. Okay, so this might seem a bit strange, but if you sort of look at the destructors, the first and second function, the encoding becomes clear. So let's run with it for now, right? Let's say I define a function called pair, which is just this function, right? Which is the same as what I've written here. So it takes two arguments, f and s, for the two components, and then returns you a pair value. So this term sort of represents the pair value. And the idea here is we take this Boolean and apply it to f and s, right? So whatever is printed below is not important. Okay, so let's look at how this actually looks when we evaluate, right? So we have a function pair, and we have two components, v and w. So I'm going to construct a pair with v and w. So I apply this pair function on v and w, and I evaluate it. So if you look at the result of the evaluation, you will see that what you end up having is a term which takes a Boolean value and then applies it to v and w. So v and w are free variables here. So you can sort of imagine that they are in the environment, right? So they're just there. And if you ask for any one of these components, you will get v or w. So as I said, v is a Boolean function. I've been repeating Boolean, 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 but this is just a convention, right? There is no type safety. So we are studying untyped lambda calculus. So we can't say, oh, this is a function that takes a Boolean and then does something with it, right? We have no type safety. When I say Boolean, it's sort of a convention that we have to follow. If you pass something else there, it will just go wrong. But for the study, right, all of this encoding lecture, we will sort of assume that we will only do the right thing, because we don't have type safety, so we can't put static guarantees on what is allowed and what is not. Okay. So here is the accessor functions. So recall that the pair value itself is this term, right, which takes a Boolean and applies the Boolean to first and second, where v and w are the first and second elements of the pair. And we did study something that looks very similar to this when we studied Booleans, right? So imagine what happens if b is true. If this b is true, then what you get is v back, right? We get the first element back. And if this b is false, then you get the second element back, right? So because that is how true and false values work in this encoding. So this is precisely how we will define the first and second functions, right? What first does, I keep doing this again and again, so let me try to slowly do it. What first does is it takes a pair and then applies true to it. So what happens? Let's assume that the pair is this pair. When you apply true to this term, true gets substituted here. So what you will get is true VW. So you'll get V out, right? And similarly, let's say we are going to do second on this pair. So if you do second, this will become false and you'll get W back. Okay, that's the idea. So we are sort of encoding the fact that we want to extract the first and the second by using true and false. Okay, so here is the encoding of first and second. This encoding is just the same as this, right? So I have a lambda p, and I apply p to true. Second is lambda p, apply p to false. Okay, so that's done. So let's look at how this actually works in practice. So here is a evaluation of a lambda term, where the first thing I do is I construct a pair with v and w, right? So I construct a pair, and I extract the first element of that pair, right? So if you run this, you can see that what we extracted is v. So what has happened? So this is the first function, right? It takes a pair and then applies the true value to it, right? This is the constructor of the pair, and these are the pair values, right? So first we construct, if you reduce this one, first we construct the pair, right? And then we extract the first element using here. But this doesn't happen in this order because we are using normal order evaluation, and we first apply the whole term to this P. So the evaluation might not correspond to your intuitive understanding of what I explained, which is first construct the pair and then destruct it. But the result is the same, right? So when you extract the first element of a pair with V and W, you get V back. And similarly, when you extract the second element of a pair with V and W, you get W back. Okay, so that's the idea. So this is how we construct pairs. So that is constructor and destructor, right? And you might want to implement other functions on top. You might want to do other things that you might want to do with pairs. So one thing you want to do is to implement something like a swap function. So a swap function takes a pair x and y and returns you a pair yx, right? This is the whole implementation of that function in Ocaml. So if I can encode it in Ocaml, I should be able to encode it in Lambda calculus as well. So so what is happening here? So if you sort of imagine this to be P, right? If you imagine this to be P, then swap can be implemented as this, right? So it's the second of P and then the first of P, right? So you take a P, you return a new pair where the first component is the second of P and the second component is the first of P, right? So we explicitly deconstructed the pair and wrote it out explicitly, but you can also write it like this because we have functions second and first. And this is precisely the implementation of swap function in Lambda calculus. So what does swap take? Swap takes a pair, right? It has to take an input pair as a first input. And what does it return? It returns a pair, right? And our encoding of pair is a function that takes a Boolean, right? So here is a function that takes a Boolean, right? So this whole thing is the resultant pair, right? This is the input P that corresponds to this P, and this whole term corresponds to this term here, right? And what do we do here? All we do is you take this Boolean, right? In the resultant pair, if the first component is requested, return the second component of the original pair, right? Which is the same as this one. And if the second component is requested, where this will be false, you actually return the first component of the original pair, right? So, and that's the encoding. And here is the implementation of the encoding in Ocaml, but this is one-to-one corresponding to this definition that I've written down here. Okay, so let's see how this works in practice. So what I'm going to do is I'm going to swap V and W. I'm going to extract the first component. So what will be the result? You can type the messages there. What's the result of this evaluation? Yeah, okay, good. I'm asking these questions because I just want some feedback, right? So otherwise, it's like talking to a wall. So thanks for the response. Do interact, right? So if I ask questions, even if you're not inclined to, even if attempt to have some interaction in the class, right? So otherwise, it'll be boring both for you and me. Let's put it that way. Okay, so here's the actual evaluation of that term. So you can see that first is here, and I apply swap to the pair that I construct using V and W. So if you run this, you get W back. So you can implement arbitrary functions that operate over pairs just using this idea. The core idea is this, right? There is, when you construct these pairs, there is a constructor and a destructor. and we've cleverly encoded the constructor and destructor using this function representation that takes a Boolean as an input. Okay, so that is pairs, right? So we've seen Booleans, we've seen simple data types. We also have lots of other data types, primitive data types in Ocaml, right? In particular, we have numbers. We have zeros, ones, and whatnot. We don't have zeros and ones in Lambda calculus. It turns out that you can actually encode zeros and ones using this very clever encoding called church numerals, right? We will keep coming back to this idea of church numerals even in the later lecture. So it's a very clever encoding. So let's and it's a lot of fun. So what is a church numeral? Church numeral is just a way of encoding natural numbers by using functions, right? And just like we had a representation of a pair, which is a function that takes a single argument Boolean and does something with it, right? For natural numbers, what we will do is we will represent that as a function that takes two arguments, right? And the idea is that the first argument is the successor function, right? It is the successor function that given a number adds one to it, right? We studied successor in Ocaml, like the suc function. So imagine that S is the successor function, represents the successor function, and Z is the representation of 0. We are not actually going to care about what the concrete thing Z is, but we are just going to say Z is 0, right? So we represent the natural number 0 as a function that takes the successor and the 0, right? And then just return 0, because that is 0. How do you represent 1? 1 is also a function that takes a successor and a 0, and it applies the successor once on 0, right? So there is 1s, so we say that that encodes 1, and 2 is a function that takes two arguments, successor and 0, and there are two s's. So the way to read this is you first apply s on z to get 1, right? And you apply s on 1 to get 2. So these are all conventions that I'm piling on, but there is no semantics beyond just the term that I've written down, right? That's just a syntactic term. So I'm giving you all these intuitions, but the term itself is just whatever it is, right? It's just a syntax. And 3 is 3 applications of s on z. And similarly, n is any natural number n is a function that takes a successor and a z and applies s n times to z, right? It's the number of s's that we count, right? So if you have n s's, then the number that it represents is n, right? That's the encoding that we go for. Can we write higher order functions here? S and Z are functions, right? We have nothing else here. So everything is a higher order functions. As you will see in what we do with these numbers, right? We will keep passing higher order functions over there. So S and Z will be passed other functions. Yeah, you can, we will get to something like that. Yeah, so 3 to Z does not, okay, really good questions. A few questions, right? I will. So I answered Sarthak's question. Can we write higher order functions here? Yes, you can. Anirudh's question is 3 to z equals 5. 3 is a function, right? It takes s and z, right? So if you apply 3 to 2, so you are applying this term where you're substituting for s, right? It won't type check, but I'll tell you how to do additions, Anirudh. So this is not the thing that you've written is not going to type check, but we will see additions. So it will work out. So is it a coincidence that 0 is alpha equivalent to false? It is a coincidence. Good question. So it is really a coincidence. So this has nothing to do with the fact that in C we use 0 for false, right? It's just a pure coincidence. Okay, good observation there. Okay, so we've encoded church numerals, right? Again, this is just writing down some terms. If you cannot do the things that you can do with natural numbers, this is not natural numbers. In particular, I want to do addition, multiplication, all the beautiful things that I want to do with natural numbers, right? Let's slowly look at how to do all of these. So here is just the encoding of 0, 1, 2, 3, so that I can use them later. Okay. So quick question. So what will be the Ocaml type of church encoded natural number 2? So this church encoded natural number 2 is fun s arrow fun z s of z, right? What will be its type? So it's one of these answers. What I'm asking is, if you wrote down this function in Ocaml, right, what will be the type of that term? Yeah, good. So good answers. So the term will be, the type will be this one, right? Why? Because you take a lambda s as an argument. So there is a function and you're using that as a function. Oops. And you take a lambda z as an argument and you're applying s to z. So s has to be a function, right? Which is applied to z. So the argument type of s has to match the type of z. And the result type is again applied to s, right? So it must be the fact that the argument type and the result type are the same for s, and the argument type is the same for z. So that's why you arrive at this one. Okay. Yeah. Okay. So let me try a little variant on this. So let me remove this. What is the type of this one? Again, the answer is there. Right. So yeah, good. So good answers. So now the point is, S is a function, right? You pick the most general type of that function, alpha to beta, right? And Z is applied. Sorry, S is applied to Z. So Z's type should match S's argument type. So that only constrains the function type to this one. So S is alpha to beta, and good answers. Good. So let me put it back. I'm happy that you're following very closely. So, okay, so that's the answer. So, okay, so let's start implementing things on functions, right? If I just gave you natural numbers and I gave you no operators on natural numbers, what use is it, right? So the point of having natural numbers is to do addition and subtraction and multiplication and so on. So let's look at a really simple function first. First thing I want to do is to implement successor function. So given some natural number 5, let's say 5, I want it to return 6, right? So how do you do this? So successor function takes an integer, returns an integer, right? So in Ocaml, but in Lambda calculus, it takes a natural number n, and it has to return a natural number. We know that natural numbers are encoded as functions that take two arguments s and z, right? And what we are doing here is intuitively, right? So if any natural number, let's say 5, is represented with the 5 s's, right? If I read the term, there will be 5 s's and a z. The successor contains one more s on the outside, right? It will contain 6 s's and a z. So the whole point is I want to add one more s on the outside. So it's like a wrapping this number which has 5 s's with one more wrapper which is an s, and that is 6. And this is what we try to do here, right? So this number, natural number input, I know is a function that takes an s and a z. So I apply s and a z. So to get to remove the lambdas, right? But what I will have is, if the function is 5, I'll have 5 s's now and a z, right? I add one more s on the outside, and that gives me the successor, right? And we are applying this here precisely because n is also a function that takes two arguments, right? And applying s and z removes it such that all you have is free variables. So it will be a term that is s applied to s applied to s applied to s applied to z, and we are adding one more s here, and then we are wrapping it back in a lambda s and z, right? Now you get the number out. Again, I'm sort of explaining it. It is better to actually see it in practice, right? So we can compute with these encodings that we've defined here. So here is the encoding of successor, just like it is described here, right? And the successor of 0 is 1, right? So we know, so let's see how it works out, right? This is 0. S of z is 0, right? And this is the successor definition, right? It takes an n, s and z, and then adds a outer s. So first thing we do is we substitute this term for n, right? Wherever n is, you substitute that one. So n is here. So you substitute 0 at that position, right? And then we are using normal order reduction. So we go inside the lambda term and reduce it. So we can see that there is an application here, right? And we go ahead and do the application. So substitute s for s. We are not using s in the body, so s is gone. And substitute z for z, and we just have z, right? So so that in 2 steps gives you just a z. And we have an outer s, right? That just sits here, right? We have it here. So the final term you get is lambda s, lambda z, sc. And that's 1, right? That is the encoding that we had. So we have actually defined a successor function that given any number, right? If I give, say 3, it gives me 4. So 3 is 1, 2, 3 ss, right? And the result has 1, 2, 3, 4 ss. So so you can apply this on any number and it will just add an s on the outside. Okay, so that's successor. The other thing that you can do on natural numbers is perform a test, right? I want to check whether some number is 0 or 1 or 2. It turns out that you can encode all these checks by having this primitive check for 0. So all I want to do is given a number, check whether the number is 0. I call that function is 0, right? And what is in Ocaml, what does is0 do? Is0 takes a natural number and returns you a Boolean value, right? True or false. So in lambda calculus, we encode it such that it is a function that takes a natural number, right? N is a natural number. And if you think about how natural numbers are encoded, they are encoded with as a function that takes 2 arguments, s and a z, right? And you apply s's arbitrary number of times, right? It could be arbitrary number of times based on the value of n. And then finally, there is a z, right? So s is a function, right? S takes single argument and returns you a single result. So with that, what we are going to do is something very clever. So given an n, for s, pass this function, right? That takes any value and then return false. The idea here is we are testing for is 0, right? If you, in the encoding of the number, if there is even a single s, we just want to return false, right? So that's the idea. If there is no ss, then is0 is 0, right? So then we return true. So we cleverly use the function s and z to test whether a particular number is 0, right? So that's the encoding. Let's actually see how it works in practice. It will become clear. So here is the Ocaml version of this one written down. So now let's check whether 0 is 0, right? Okay, so what is happening here? So we have the 0 here, right? Is 0 takes a natural number, right? Here, and then applies this function, right? Which is take any argument, right? That is just going to be substituted where the s is present. Take any argument and then just return false, right? The idea is if you happen to find an s in the term, it is just false. So that is what precisely is 0 is saying. And this is just the encoding of true. Okay. So what happens here? We first substitute 0 for n, right? N is here. So we get n, and this term, which is the same as this term, and the term here, which is true here, right? And now we have an application as well. This is A applied to B applied to C. So first apply A to B. So for S, substitute this whole term, but we don't have any S's in the body. So that's ignored, right? So that just goes away. So you have lambda ZZ true. So if you apply true to Z, you just get true back. So is 0 of 0 evaluates to true. So let's try is 0 of 1, right? So the same thing. So we have 1 here. We have the is 0 function here. So first substitute for n 1. So you get 1 for n, right? And these two terms are the same as these two terms, right? Now this is again A, B, C. First apply A to B. Wherever you find an S, substitute this term, right? So this gets substituted. We have an S here, right? So it gets substituted in the body, right? What do we have? This is the clever bit, right? We have a function that takes whatever argument and then just returns false. The false is encoded here, right? So you have this function which takes a lambda z, and then whatever you pass, it is going to just return false here. And that's the clever bit. And if you now apply true here, true gets substituted for z. So you get true here for this z. And I'm just going to ignore true here, right? That's what is happening here. So this true value gets substituted for this y, and we don't use y in the body. And all I'm doing is, it's a constant function at that point. You give me anything, I'm just going to return you a false. And this false gets returned. You can sort of imagine this works for arbitrary numbers, right? So just to complete that argument, is 0 of 1 is false, is what it's saying. Is 0 of 0 is true, is 0 of 1 is false. If you apply 2, you get the same idea. You can apply it for arbitrary numbers, right? I don't have any numbers beyond 3, constants beyond 3. But you get the idea. Everything is a false. Okay, so we've defined the is 0 function, which is going to be a test that returns either true or false. So, okay, so we've defined successor, we've defined is 0, which is a test for a natural number. The common thing that we do on natural numbers is additions and multiplications, right? So let's define addition and multiplication. Again, the encoding is quite clever, but I'll sort of try to give you an intuition, but the concrete steps are better explained by looking at an example. So what's the intuition of a plus, right? Plus takes two numbers, right? Two natural numbers and returns you a natural number, right? So it is a function that goes from natural number to natural number and returns a natural number. And in our lambda encoding, how do we represent numbers? It is the number of s's, right? If I give you 1 which has 1 s and 2 which has 2 s's, then the result should have 3 s's applied to z, right? That's what we are going to go for. And the idea is this. So so let's actually walk through the example, right? So as I mentioned, plus is a function that takes two natural numbers and it's going to return a natural number, right? Just because just like how we encode natural numbers as functions that take two arguments, we have functions that take two arguments, right? And all we're doing here is so this m is a natural number, right? And that has some number of s's, and then the last one will be a 0, right? A last thing will be a 0. What we are going to do is take the 0 out, throw that away, and then just replace the 0 with whatever number of sz that n has, right? So if 1 has sz, 1 is represented as, let me just write it out. If 1 is represented as sc, I'm ignoring certain things, but that's not important. 2 is represented as s of z, right? I'm going to say 1 plus 2 is replace the z with this term, right? Take the z out, right? And replace that with whatever I have here. What that gives me is s of this s comes from here, right? This goes away, and we are replacing that with this term. So we get s of z. So s of z, and that is 3. And that is precisely what we are doing in terms of plus. So I have the first number. I just keep the s's just like it is. But where z would be there, I just replace that with the body of the number n. Okay, so if you have n s's there, it will be n s's followed by a z. Okay, so that's addition. So all we are doing is we are taking out the 0 and then replacing that with whatever the body of the second number is. Multiplication can be understood as something very similar. So instead of replacing the 0 number, replace the s's, right? So what is happening here is, let's say I have some interesting number. Let's say I have 2, so which is s of z, right? I'm going to multiply that with 3. S of z. Okay, so what I'm going to do in multiplication is wherever I find an s in the original number, I'm going to replace that with these number of s's from the second number, right? So if you find an s here, replace that with the number of s's that you find in the second number. So essentially 2 times 3 is going to be, for this one s, replace this with so many number of s's, right? And for the second s, again replace that with so many number of s's, right? And then a z. And yeah, of course, brackets are, you just get the bracketing right. So the idea is 1, 2, 3, 4, 5, 6, and 2 times 3 is 6, right? So that's the intuition behind it. I'm of course not being precise here, but that is precisely what is happening in the definition of multiplication. So wherever you find the s, replace that with the number of s's that you will find in the second number. Okay. Okay, so with that, we can actually look at an example to make our understanding a bit more clear. So this term is precisely the same term here. So I defined plus and multiplication. So let's do 1 plus 2. Okay. So 1 plus 2, the solution is 3, right? And yeah, I'm not going to walk through all of this. I recommend you to follow along what I mentioned, the intuition that I mentioned, right? So the idea is that you take the first number, right? You take the first number, which is 1, and then replace the z with the body of this number. So you have s applied to s of z, and you get 3 as a result. Okay, so that's 3. The high level concept here is this, right? So this actually proves that 1 plus 2 is 3. We are not sort of taking, I mean, because we've encoded 1, 2, and 3 as counting the number of s's. The fact that I am able to evaluate this using 1 and 2 to get this particular term, which is 3, is a proof that 1 plus 2 is 3. And these are the steps here defined here are the proof steps for getting from 1 plus 2 to 3. And using lambda calculus, we can build an entire theory of arithmetic. So we can prove all of the things about natural numbers that we want to do using using lambda calculus, right? So if you want to prove a theorem about something, you can use lambda calculus to prove it with the assistance of a computer, right? You can do paper proofs using our intuitions and such, but we are not using intuitions here, right? The only thing that we've sort of assumed is the fact that count the number of S's in the body, and that is going to represent the natural number. Everything else we've just encoded from scratch. If you believe lambda calculus is correct and our encoding is sort of natural, then just by doing that, we've actually proved 1 plus 2 is 3. Right? So I think that's the power of lambda calculus. You can sort of prove higher level concepts without appealing to intuitions. Right? Okay. So again, so here is multiplication. So I'm multiplying 2 times 3. I'm not going to work through this. I don't recommend you to work through all of the details, but the intuition is important, right? Just the intuition that I described earlier. So 2 times 3 is 6. So you'll see 1, 2, 3, 4, 5, 6 C's. Right. So here we proved 2 times 3 is 6. Okay. So we've done successor before. Successor is just adding one S in front of a term, right? You have a body of SS, you add one S to the front, you get a successor. Predecessor, it turns out, is quite tricky. So it's like peeling an onion, right? So you have a number of S's, you have to peel an onion out. And peeling is not a primitive operation that we have. So adding a layer is application, right? Lambda calculus gives you application. I can do application as a primitive operation. But peeling something is not a primitive operation in lambda calculus, because everything is a function application. If you apply a function, it's not like you can take it apart. And for this reason, predecessor turns out to be much more tricky than a successor. So we will use a very clever trick here, right? What we will do is we will use an encoding using a pair, where the idea is the pair will always represent a number and its predecessor together, right? So this is the intuition. Let's see how it works in practice. So I define ZZ as a term that is a pair with 0 and 0. The idea here is the predecessor of 0 is 0. We are using natural numbers, right? So when you get to 0, we don't have a notion of what a predecessor of 0 is. So we just happen to use 0, right? And for any other number, right? So given a pair of that looks something like this, the successor is defined such that it is the second component of P, which is this component, right? And the first component plus 1. Sorry, the second component. Sorry, 1 plus the second component. So this. So okay, so let me try to give a concrete example, and it will make sense. So we define 0, 0 as a pair with 0, 0. Okay, so that's the basic definition here, right? 0, 0 is 0, 0. If you apply SS to 0, 0, it takes the second component of the pair, which is 0, right? And the first component is just the second component of the original pair. So we get 0 here. And the second component of this new one is 1 plus the second component, right? 1 plus the second component, so 1. And if you apply one more SS here, so you take the second component, that becomes the first component. You take the second component, add 1 to it, that becomes the second component. So the idea here is every term that is a pair here contains the number as the second component and its predecessor, right? For 0, 0, it is odd because we don't have a predecessor for 0. But for every other number, it is 1 and its previous number 0, 2, previous number 1, 3, previous number 2, and so on. So this is an intermediate step for us to help define the predecessor, right? So we are using this clever encoding. We will see how we actually use this. The intuition is, once you actually build this proof up, if you need to get the predecessor of 3, if you are able to build this from ground up, then you know that the first component will have the predecessor, right? If I need to get the predecessor of 3, it is going to be 2. That is what we are going to get towards. And how do we get to that? The predecessor function, right? What is a predecessor function? Predecessor function takes a natural number and returns a natural number, which is a predecessor, right? So this is the clever bit, right? So we take the natural number for the predecessor, give in the natural number, wherever s is found, use this function ss, right? And wherever z is found, use this function, use this term zz, right? So this builds up a proof from the bottom up. So if M contains 2 S's, right, it builds the proof from bottom up saying the predecessor of 0, 0 is 0 is 0, 1 is 0, 2 is 1. So it builds this whole term up from bottom up. So the term that you've built for 2, let's say this M is 2, is a pair which contains 2 as the second component, right? And then has 1 as the first component. And we are extracting that first here, right? So that's the clever bit. So you use the constructor to build the proof from bottom up. So anytime you require a predecessor, what you're doing, yeah, so you need a different encoding for negative number. I'm just looking at the question, sir, but since the base case is 0, 0, how are we going to define negative numbers? You can define negative numbers, but you have to go for a different encoding. So we cannot use the natural number encoding here, right? So we won't see negative numbers here, but that's the idea. Okay, so how does this actually work? So I've defined ZZ and SS, right? And then I've defined a predecessor here, which is just the encoding of whatever is here. That's 2 predecessor of 3, right? And what you get is 2 out, and let's do predecessor of 0, you get 0 out. So predecessor of 0 sort of is 0 because we are operating with natural numbers. There is a lower bound, right? And we cannot go below that. And essentially, when we ask for 3, what we are doing is we first build 0, 0. Then we say, oh, 0, 1. Then we say 1, 2. Then we say 2, 3. And that's the term that we have finally. And we extract the first component of the term, which is 2. And that happens to be this term. Okay, so again, this is sort of works as expected, but this is not how you will implement it in practice, right? If you want to implement predecessor in your real language, this is not what we do. So this is sort of just think about these as proofs of predecessor, right? Rather than encoding predecessors in practice. Okay. So yeah, so now you can use the predecessor to implement subtraction. So the idea is that with addition, what we did is we replaced the 0 term with the number of s's, right? But in subtraction, you have to take out. So if I subtract, say, if I want to do m minus n, if I want to do m minus n, m is some number that has some number of s's, right? And n is some number that represents the number of s's that needs to be taken out of m. So all we do here is apply the predecessor function n times on m, right? So this is like saying take the number m, right, and apply n times the predecessor function. This is a bit tricky. This is like multiplication, a little bit like multiplication, but it works out. I think if you sort of stare at it offline, you will see how it works. Again, I don't want you to focus too deeply on how we came to encode this. I just want you to take away that these things can be encoded. Okay, so that's the idea there. Why can't we implement numbers as n tuples as? You can do that. Yeah, you can certainly do bitwise booleans as well. So these encodings are just one way of doing it, right? So there are several different ways to encode numbers. It depends on what you want to show, right? So in real machines, right, we encode everything as Boolean because um, that is how they are represented underneath, right? So essentially, all these machines work on Booleans. They operate on bits, but we don't operate on bits here. We operate on higher level concepts. So it is better to encode. It depends on what you want to do with those things, right? Um, Here we want to just show how addition and subtraction and all these things work. So you can encode Booleans, but that would be just um, yeah, that would possibly allow more things to be encoded. But if you just want to encode addition and subtraction at the end of the day, I don't see a benefit in encoding everything as Boolean. You can do bitwise operations, but of course you can't do bitwise operations here. Anyway, so getting back to this, right? So here is an implementation of subtraction. It's very large. Details are not important, but subtraction works out, right? If you do 3 minus 2, you get 1. But subtraction doesn't work out for 2 minus 3, right? We have natural numbers. So yeah, 2 minus 4 will be 0. 2 minus 3 will be 0 because um, so what is it doing? What is it doing, right? The way we encoded it is you have 2, which contains 2 s's, and we are saying take 3 s's out of this 2. So we don't have 3 s's, so we can only take out 2, and we stop at 0. Right? So this sort of gives you naturally gives you what should happen at the limits, right? So once you hit a 0, you just stop. Okay, I think I'll continue with the rest of the things in the next class. I'll stop here. We've seen a couple of things. I hope that I can finish this lecture in the next class. Questions? Any questions? No questions? You can also ask questions on Slack. Okay, in that case, I'll stop now. Thank you very much.